Hi guys, it's Dr. Justin Souther here, going through some of your tutorial assignment questions. This is a particularly fantastic question because it's a chain rule, but because we're looking at the second order partial derivative here, it's a chain rule on steroids. So it's a really good question, it's a really important question. You do need to know how to be able to do this one. There are a couple of them assigned in the assignment, and there's lots more to practice as well. Right, so we've got that z is equal to some function in two variables x and y. We're not told what the function is, but let's go right ahead and start drawing our tree diagram. So we know that z is a function of x and y, and we're told that x, and here we are given the functions, x is a function of r and s, and y is also a function of r and s. So we've got our typical tree diagram here, splitting twice and twice into 2 and 2 again, and we're asked to find the second derivative of z first with respect to, now remember the order here, when we've got in this notation we read right to left, we're first going to differentiate with respect to s, and then we're going to differentiate with respect to r. It doesn't really matter because we've got Clairaut's theorem, but let's do it in the order that they suggest here. I'm going to use the simpler notation. I'm going to say we want to, well, eventually we want to find this is equal to derivative of z first with respect to s partially and then with respect to r. Now before we can find the second derivative, we need to find the first derivative. So we're looking for the derivative of z with respect to s, and that's what our tree diagram over here is going to give us, and that's equal to, well, all the paths to s. There's that path over there, and there's this path over here. So that's going to give us z with respect to x times x with respect to s plus z with respect to y times y with respect to s. Now, we don't know what the function z is, so we can't actually find an explicit formula for this, so we're going to leave that just as it is at the moment, but we can find the partial derivative of x with respect to s because we've got the function there. So this is equal to z differentiated with respect to x times derivative of this with respect to s, that's a constant, so its derivative is 0, that's s squared, so that's times 2s, plus zy, again, we don't know what z actually is, so we just leave it as zy, times the derivative of y with respect to s, and now that's just going to be times 2r. Now, we're essentially halfway there because we found the first derivative. Now we want to find the second derivative. So we want to find the derivative of z with respect to x, and now we want to differentiate with respect to r. Now, how are we going to do that? We've got to differentiate a sum, so we can just differentiate each term in the sum, but each term is a product. So we're going to differentiate this guy over here using the product rule. This is a product. I hope that's not too small on the video to see. So the product rule says we differentiate the first. Remember, we're differentiating now with respect to r. So the derivative of the first is zxr multiplied by the second untouched, so that's 2s, plus the first untouched, so that's just z subscript x, times by the derivative of the second. And the derivative of 2s with respect to r is, quite conveniently, 0, because it's just a constant. Plus, now we need to do the same thing with this thing over here. This is also a product, so we differentiate the first, we get z subscript yr, multiplied by the second untouched, 2r, plus the first untouched, z subscript y, multiplied by the derivative of the second. Now we're differentiating with respect to r, so this one is not 0. The derivative of 2r with respect to r is 2. Right, we're getting closer and closer and closer. Now, what we need to do, this is where things really get interesting, and this is why I say it's the chain rule on steroids, because this thing over here is the tricky one. We want to differentiate zx with respect to r. Now, what is zx? We don't know exactly what z is, but we know we can differentiate it with respect to x. And when we differentiate it with respect to x, we're left with another function. And this function, z differentiated with respect to x, is also going to be a function of x and y. The y's haven't disappeared, we've just differentiated with respect to x, so we're still going to potentially have some y's, have some x's and also some y's. Zx, this derivative, is a function of xy. And of course, x is still a function of r and s, and y is still a function of r and s. Right, so zx differentiated with respect to r, we have to use the chain rule. Start at zx, how many ways are there of getting to r? Well, there are these two ways over here. So, this is equal to, just this thing over here is equal to these two chains. These two chains. It's zx with respect to x, that's that part of the chain there, times by the derivative of x with respect to r, that's that part of the chain over there, plus this link here, zx differentiated with respect to y, times y differentiated with respect to r. That is, this whole piece here is that over there. And of course we need to multiply that by 2s. Plus, well, that one disappears quite nicely. Plus, we've got to do the same thing for this over here. Z, when we differentiate it with respect to y, we end up with a new function, which is also a function of x and y. Once again, x is a function of r and s, y is a function of r and s, and we can follow all the chains down to r, and we get zy differentiated with respect to x times x differentiated with respect to r, plus zy differentiated with respect to y times y differentiated with respect to r. And again, this whole thing here is simply this second partial derivative over there. We still need to multiply it by 2r, and we still need to add z differentiated with respect to y times 2. Okay, we're very close now. We can't do anything about this. We don't know what the function actually looks like because we don't know what z looks like, but we can differentiate that. So we get z double derivative xx, xr, so x differentiated with respect to r is going to be 2r, plus z subscript xy, y differentiated with respect to r is going to be 2s, and that's all still multiplied by 2s, plus 2 subscript yx, x differentiated with respect to r is 2r, plus z subscript yy, y differentiated with respect to r is going to be 2s, and we're going to multiply that by 2r, plus, and we've still got this over here, z differentiated with respect to y times 2. Okay, let's just see if we can neaten this up a little bit. Let's multiply this in here, so we get 4rs times z subscript xx. Now we've got 4s squared times zxy, and we've got 4r squared times zyx. And remember, Clairaut's theorem says that these two guys are the same, so we can write that as, here's our 4, let's write this 4r squared first, 4r squared plus 4s squared, that comes from there, and both of those are multiplied by z subscript xy. Then we've got this term over here, which is going to give us 4rs multiplied by z subscript yy, and of course don't forget about that little 2z subscript y over there. And that's your final answer. It's quite a lot of work, it's quite detailed, there's multiple uses of the chain rule, but it is a very important example, which is why I wanted to go through it quite slowly.